Our next speaker is Miriam Schuster from the Darmstadt Glass Competence Center. She completed her PhD in 2022 and has since then co-led the Glass and Polymer Group at the Glass Competence Center, focusing on the circularity and glass product. Additionally, she's active in standardization and structural engineering associations. And additionally, she's a fantastic mentor for the students we've been exchanging. So this is leadership right there in action. Without further ado, Miriam, the floor is yours.
Thank you, Sophie, for this very nice introduction, and welcome to my presentation with the title Heat Treatment of Pre-Damaged Soda Lime Silicate Glass and its Influence on Glass Strength. So this work was not only done by myself, but in collaboration with a master's student called Felix Dimmerling and colleagues from my institute, Hans Scholz, and also Professor Michael Krause. So my presentation is divided into different chapters. I will start with a short motivation, then we have a quick look into the theory of crack healing through temperature treatment. Then I will present the experimental investigations that we conducted. I will present the results and close with a summary and outlook. So I think we all know that glass is a very interesting material, especially for buildings and facades, because it enables the daylight to come into the building, and hence we find approximately 48 to 100% of glass in facades. And the facade is also the outer skin of a building, which means that it highly influences the operational energy that you use during the use time of the building. And since our glass products have developed over the past decades, we are expecting a very high renovation wave where the old products are exchanged with newer products that have a better thermal performance. And hence I found the number of 1.1 million tons of glass a year from old buildings that will be available in future. In addition, we have the Circular Economy Action Plan, which says that we shall minimize our resource consumption and also the waste. And to do so, we have different possibilities. And from the CO2 and material use point of view, I think that the reuse and remanufacturing is the most effective one, and that's why I focus on that. When we want to reuse glass or remanufacture something with old glass, then we need to know their performance. And one of the most important mechanical parameters is the strength. And in this picture, we see a glass with a scratch. In the light gray, we have the glass surface. And what our naked eye can see is the lateral crack with the chipping. What the naked eye cannot see is this median deep crack, which goes through the thickness of the glass, and exactly that crack is responsible for the strength of our glass. And having a look at the fracture mechanics, we see this very short formula, which says that K1, which is the stress intensity factor, can be calculated from the applied stress. This is the stress that acts perpendicular to the crack flanks. A geometrical factor, which is dependent on the geometry of the crack, and also the depth of this median crack. In the graph, we see two gray lines. These are two different geometries for the crack. So we have the long surface crack and the half penny crack shown here. And I also marked the 45 megapascals on the y-axis, which is the stress that I want to apply without failure. And here we see that for the long surface crack, the depth of the median crack is limited to 70.3 micrometers, so that no failure occurs, which is quite small actually. We also know that the scratches are unavoidable, so they can also already be introduced during the production, but also during the processing, during installation, during the use phase. For example, when you're imagining having walkable glazings, or even during cleaning, you can introduce scratches. And what now comes in addition to this is the deconstruction of the glazing from the building, maybe a disassembly, another transportation, a reprocessing, and so on. So we have a lot of different steps that might introduce new scratches and hence have an effect on the strength. And a former colleague from our institute, Sebastian Schuler, did a lot of investigations on the strength on glass, which was damaged. And I want to highlight here only one or two cases. So here we have glass that was treated with a squeegee. A squeegee is this green tool here at the top, and it was used to remove screed or plaster from the glass. And we see that those glass only had a strength of around 10 to 20 megapascal, which is much lower than the characteristic strength value of new annealed glass that we find in standards, and is usually 45 megapascals. So when we want to reuse the glass or remanufacture with it, we have two options. The first one is we use a smaller or reduced strength value during the design, but then we need to know how much do we reduce the strength. Or the second one is we try to restore the strength of that glass. And in order to restore the strength, there exist different possibilities in literature, and one of them is heat treatment. And what can happen during a heat treatment is a viscous flow. And yeah, this means that a sharp crack, as shown in the picture, in the first picture, can smoothen out and the stresses around the crack are relaxing. The viscous flow can bridge the crack, the deepness of the crack can be reduced, or it can even completely filled up. And viscosity is dependent on different parameters. They are, for example, temperature, time, and humidity. The higher the temperature, the higher the time, and the higher the humidity, the lower the viscosity, and hence we expect a higher viscous flow for that. Now I come to our experimental investigations. So we investigated soda lime silicate glass. This was all new glass. It was annealed glass. The samples had dimensions of 8 by 8 centimeters and a thickness of 6 millimeters. Then we introduced a pre-damage in the middle of the surface. We stored our samples. Then we had a heat treatment. After the heat treatments, we performed ring-on-ring tests in order to determine the strength. And after the ring-on-ring test, we looked at the fragments and measured the crack depth. So for the pre-damage, we used the universal surface tester, and the pre-damage was always introduced on the thin side. And yeah, the indenter we used was made of diamond, had an angle of 120 degrees and a 5 micrometer radius. The length of the introduced scratch was approximately 4 millimeters. The force that we applied was 500 millinewton, and the velocity was 0.1 millimeters per second. After storage, we then started with the heat treatments, and you see here our 8 series that we conducted. The last series, R1, is our reference series, so for that case, we introduced the scratch just as shown on the slide before, but there was no heat treatment. We directly started then with the ring-on-ring tests with that. The rest of the series were heat-treated series. We have investigated 3 different temperatures. The lowest was 350 degrees Celsius. Then we had one with 540 degrees Celsius and one with 640 degrees Celsius. And the duration of the treatment also varied between 1 and 8 hours, and for all those series or all the 3 temperature, we also investigated a 4-hour treatment just to better compare the results afterwards. For each series, we had 32 samples, and we used 2 different ovens for our investigations just due to time issues. Here we see the 2 ovens, and what is important, or was important for us, was that one series was treated at once, so we had each time 32 samples in the oven. For 3 series, we also had the possibility to record the time temperature curves, and yeah, we see the results here. So the heating was always conducted with 10 Kelvin per minute. Then we had the heat treatment period, and then the cooling down was performed very slowly, just to guarantee that our samples are still annealed after the treatment. And we also checked this with scalp measurements, so this was effectively also the case. After the heat treatment, we performed the ring-on-ring tests based on the 1288. The radius of the support ring was 30 millimeters, the one of the loading ring 6 millimeters. We had a stress rate of 2 megapascal per second, and the squelch, of course, was always on the tensile side. From the fracture force, we calculated the fracture stress, and then we did a statistical evaluation with a two-parametric Weibull distribution function. After the ring-on-ring test, we looked at the fragments and searched for the fracture mirror. Then we zoomed in. So this is a zoom from the other picture, and then we measured here the critical crack depth with the microscopy. So let's come to the results. So in the table, we see now all the fracture stresses already evaluated. We have a lot of numbers here. I will not present all of them. But in fact, we have the first column, which are the mean fracture stresses for all the series. Then the second one is the mean divided by the mean from our reference series. And I think that's the most interesting. I will explain this later. Then we have the standard deviation, the coefficient of variation, and then we have the results from the Weibull evaluation. So for the mean fracture stress compared to our mean fracture stress of the reference series, so the second column, we already see that we have an increase for the mean fracture stress for all the heat-treated series. Even at the low temperature of 350 degrees Celsius, we see an increase of 10%. It's low, but it's an increase. We also see that the higher the temperature, the more the mean fracture stress has increased. But we also see that the duration of the heat treatment does not really have a high influence, at least for the 350 degrees Celsius and also for the 540 degrees Celsius, we did not see a real influence. For the crack depths, I have again a lot of numbers. Also here I will only present the mean crack depth divided by the mean from the reference series. And here we see that the crack depth has reduced for all the heat-treated samples. Comparing this with the mean fracture stress, we see that the increase of the fracture stress matches the decrease of the crack depth, which is good because it somehow proves the theory that I presented at the beginning. So let's come to the summary. We pre-damaged a new soda lime silicate glass. The pre-damage was approximately 4 millimeter long, and the average crack depth was 58 micrometer. This crack depth was measured after the ring-on-ring test. We investigated 7 different temperature treatment programs, and for all of that programs, we could observe an increase in strength even at the low temperature. The increase in the mean fracture stress also matches the observation of a reduced crack depth, and we had the best results for a treatment of 4 hours at 640 degrees Celsius, where we achieved a 1.6 times strength compared to our reference series and an 0.4 times crack depth of our reference series. As an outlook, we are at the moment looking at more statistics. So we are looking at how significant our results are and how significant the correlations are. In addition, we expected to have a higher influence on the duration of the heat treatment. This was not the case, and we want to investigate this further. Why is this not the case? Was the temperature too low? Was our duration time too low, or whatever? So this is one topic we want to focus on. Then we already started a different series with another crack geometry, because the crack that we investigated here was quite small with this 58 micrometers depth. And the second series, we are investigating a crack that has a depth around 250 micrometers, so much larger. And then we also want to look at naturally aged glass, which might have different crack geometries on its surface. And finally, it's also important to scale this up. Yeah, that's it from my side. And yes, I'm happy to have some questions.